So thank you. Good afternoon. So I'm going to present you some ongoing work on the LAIBrary project, which consists in deciphering the aromatic infrared bands. And this is a combination of experimental work performed by Karine Demick and Shubha Chakraborty at the time, and many internships. So we see Clelia Bastelica and Lise von Rotel. And also some modelers, so Dominique Toublanc at IRAP, Giacomo Mulas at INAF, and some quantum chemists, so Aude Simon, Mathias Rapaccioli, Patrick Kassamschenheim, and also Giacomo, who is also in this team. So this is a work that has been supported by the ERC Nanocosmos, but also the CNES. We have some support from the OVGSO, so Observatoire Virtuel Grand Sud-Ouest, and CNES also help us with a contractor in a software engineer working on the database project. Okay, so what I'm going to present you is aromatic infrared bands. No, it doesn't work yet. So you saw them already. This set of bands observed in emission, and they are quite strong in many regions of space between 3 and 20 micron. And they are well observed by the space mission. So we had the ISO, Spitzer, Akari, and now we are working on the James Webb Space Telescope observation. And one interesting thing is that in a photodissociation region, they can be used to trace physical condition, or we hope, such as the radiation field. And you see that you can have different situations, like the Orion bar, that is the focus of the PDR for all project, in which this molecule emit and are mixed with ionized gas line that you can see here on this spectrum. And if you are in a mild reflection nebula, you don't have this ionized gas, and you observe the aromatic band with some rotational H2 line. So when we look at high spectral resolution, and that was possible with ISO SWS, you see that there are actually some structure in the line, and we see, for instance, that we have some evidence for CH aromatic stretch, but also aliphatic, and also of a feature which I'm not going to discuss here, but they indicate the presence of chemical diversity. Another thing is when we look at high spatial resolution, then we can have information on different pixels, like given by the Spitzer IRIS instrument. And you see on this NGC 7023 reflection nebula, or PDR, that the spectrum vary inside the PDR, and that indicates that there's an effect probably of the UV field, but this effect is not an excitation, not only an excitation effect, it can also be due to photoprocessing of the carriers of the band. So that leads to a quite complex situation. And now with PDR for all, we are going to combine this high spectral and high spatial view of these aromatic infrared bands. I'm not going to discuss it, that will be presented by in the presentation of Olivier and Emilie about tomorrow. So deciphering the AIB. So the big question, can we use the observed band to quantify local physical conditions, such as the UV radiation field, but also the electron density, the hydrogen density? And which feature of the spectra are related to the emission mechanism, and which can reveal molecular and chemical diversity in general? So I'm going to present you some results on the way we are facing this situation in the framework of the pH model. So the pH model is all based on the pH photophysics. So you have a molecular pH system which receive a vacuum UV photon or far UV photon, and different mechanisms can happen the molecule can get ionized, and this can have an impact on the gas heating by the photoelectric effect. The molecule can get photodissociated, and that can impact its lifetime in the different environment. And the molecule can relax the absorbed energy by radiative cooling, either in the aromatic infrared bands or other mechanisms such as the recurrent fluorescence, which I will briefly discuss. So an interesting feature of the spectroscopy of hot pHs is that the bands which are emitted change in position and in profile as a function of temperature. Well, it's not very surprising, but that has been quantified on a few species actually during my PhD. And what you can observe is that the band position can be actually shift on the temperature range that was studied with temperature, and it is about a linear trend, which you can describe by what we call an empirical anharmonicity factor. So now it means that the bands which are emitted are not a single band, but result from a combination of many bands emitted during the cooling of the molecule. So when you calculate a band profile, you have to sum all these contributions, and you have to take into account that at each temperature, the band has a specific position and width, which is related to this temperature. And a recipe has been given in the Pech et al. Paper at the time, based on the first laboratory experiment, in which you can see the different astral bands and what we expect as empirical anharmonicity factor, both for the band position and width. So that was the first approximation of this model. So now the big question in the pH model for pH. We have to understand the evolution of the charge state, of the size, of the hydrogen content, linked with aliphatic, so then it makes it more complicated. And we have to disentangle in the spectra the effect of temperature from chemical complexity, and this is this effect, this aspect, which I'm going to describe in the LAIBrary project. So the idea of the LAIBrary project is very simple, at least for the user. You have a simulator. You type your favorite molecule, your radiation field, and you get the spectrum, the infrared spectrum. So this is very nice for the user, much more complicated for the person who developed this system. So we have to get this simulator, which will send query to different databases. So for the molecular data, we need various information, which we get, for instance, from a theoretical pH database. Also some information on the spectroscopy from hot pH infrared spectroscopy database. We need to know the astrophysical radiation field, and we need an emission model that will calculate, well, actually it's more a photophysics model that will calculate the photophysics of a pH in a given environment and lead you to the emission spectrum. Okay. So first step, the theoretical spectral database. So we gather since a year information in databases, basically based on a calculation from DFT or TD-DFT. So you select, so this is the first static database in which you select a given molecule. And you can, for instance, for this coronet, you can get the absorption cross-section in the UV part. And you can here you have the radiation field of our favorite object, NGC 7023 Northwest. So calculated from using the Meudon PDR code and some idea we have about the exciting star. Here you have the absorption cross-section. So in red of the neutral coronet, in blue of the cation, you see that it's not so different. It's a UV part of the spectrum. And then you can calculate the absorption rate by multiplying both the radiation field by the absorption cross-section. And that gives you where you absorb photons. So basically you absorb photon of about 4 on 6 EV in this environment. You don't absorb so many photons at higher energy, and this is in a way good for this molecule because here you start really to seriously dissociate the molecule. And the typical time scale between the absorption of 2 UV photons is a few hours. So then we use a Monte Carlo emission model in which we describe all processes. in the framework of a microcanonical statistics. So in addition of UV absorption rate, we have dissociation rate, infrared emission rate, in the harmonic approximation, the Poincaré or recurrent fluorescence rate. And this is all given while using this harmonic density of state using the Bayer-Signard algorithm. To give you an example, so this is the cooling curve of the coronet molecule, neutral and cation, after the absorption of a 6 EV UV photon. And you see that the neutral takes more time to cool down than the cation, because this is because the neutral is very symmetric and has less channel to get out the infrared energy. This is the simulated spectrum. Well, we know this already, but the neutral from the old days of even quantum chemistry. I know Françoise and others in the room, that the neutral would emit preferentially in the CH mode and the cation in the CC mode in this range. Okay, so now we convolve all this with the absorption rate in the specific radiation field. I give you the resulting spectrum. And what I want to point here is this recurrent fluorescent channel, which is made of some electronic transitions. So first excited state. We have no information in the lab about the detailed spectroscopy of this channel. We just know it exists. And we quantify it by the microcanonical model. So we know about the position. The width is completely arbitrary, but you see that this channel is there. Not so important though for this molecule, but still much work has to be done. And there will be a presentation by Ozan Bala just after concerning carbon cluster. If we compare to the spectrum, the Spitzer I-ray spectrum, you see that it doesn't work so well for this molecule. We are not very surprised, but still you could see it could be there, but at a lower abundance. But okay, this is the first comparison. So now what on the experimental side, what can we do? So first we use Karine Lemic experiment, the Espoir setup. And at the beginning, we use the same technique that she presented also for the silicates. So make PBR palettes, put them at low temperature to study the evolution at low temperature, but we also wanted higher temperature. So we bought this environmental cell, which get us to 723K. After that, the PBR pellets start to melt and we have to stop. And we also develop a high temperature gas cell to study the spectroscopy. And this is a setup that is now starting to work. So this is a work that was published on Pyren using the KBR palette. What was nice here is to see that at low temperature, the band does not shift, it stays constant. And then you see this linear increase that start to appear. And you see here the band evolution with temperature from blue cold to the red hotter. And you see that's nicely shift. This is an easy band to study. So we decompose this band in multi-component to calculate a weighted area position and get this specific point. The gas phase start here, and you see that it follows nicely what was found in the solid phase. In the Pech et al. Model, they use this gas phase data and then just use extrapolation here. So what we would like now is to construct a full spectrum. So we want to consider not only the 4 or 5 main bands, but also all the bands that are available in the DFT calculation. So this is why we use as a point the scale DFT position. But you see, if you use the Pech et al. Slope, you will get this trend here, which is a bit far from this. So what we are going to use in the model 2 is this trend here from this DFT calculation and using the same parabolic trend here. Right, okay, some technical detail. And you see that actually the solid phase width, bandwidth for this specific band follow very well that was derived from the gas phase width. So this is the result of the model 1, in which, of course, there's a larger shift with temperature compared to model 2, in which not only the position is different, but also the trend is this is lower change with temperature. So you see the band is more to the blue and more asymmetric, okay, than the other one. Okay, so that was a simple case. Now, if we move to another band, also of Cornell, this is the CH out of plane band, and you see that it's not only one band, but you have several. So that makes the analysis more complicated. So we are thinking on how to address this. There's also some theoretical development. So Giacomo Mulas developed, and collaborators, they developed the anharmonic chaos ab initio code that try to describe all infrared transition, including bands that are that becomes active due to resonances, as well as overtone combination and different bands. And to treat the resonances, they build an effective Hamiltonian of resonating states. So this is very specific and something that you cannot find in Gaussian, for instance, even if you are running an harmonic calculation. But was validated at 0K by comparison with experimental data. And after that, there was some calculation at higher temperature on pyrene up to 523 Kelvin. You can see here the difference between this calculated spectrum and the gas phase spectrum. It's quite nice. Of course, there's still some problem, for instance, on this 3.3 micron band, the CH stretch. And what is nice also is that the code can really describe all the band coupling. You see that here you start from the three fundamental bands in this range, which are given by here. If you compare to scale DFT calculation, you have this position. This is the band that are really calculated using in the anharmonic situation. And when you increase the temperature, then you see you have a lot of contribution. And some bands stay narrower, some are getting broader, and at the end, you can even build some continuum. Okay, DFT anharmonic chaos has limitation because it makes detailed calculations, so it is limited for higher temperature and larger species. It just takes too much computational resources. So we also investigate the use of DFT molecular dynamic simulation. So in this case, you see that it's less precise on the position, but still, when you look at the trend, it's quite good. It's not for all bands, but this one is good. So you see that you have the DFT anharmonic chaos here, and then you have the MD calculation. Of course, it was shifted in position, but the relative trend is correct. And this is the gas phase slope. So you see that this is in quite good agreement. And this is about bandwidth. The gas phase you have to correct from the rotational broadening. So when you correct for the rotational broadening, you come here, which is in nice agreement with anharmonic chaos. But here you see the MD calculation are not so good. So well, anyway, there's a lot of work to do on this. We try to publish all our achievements on databases and tools. This is in construction. Right now we have a wiki page, which is open. This is the Cosmic pH portal. So we have these tools associated with databases, which I will present quickly. So one is a Cookie tool, which is a tool to import the output of quantum chemistry code into a new database, which is very nice to feed the database in a more automatic way. So we are about to release this new database. Another important thing is this is connected to the VMDC portal, for those who know this portal. So it means that the database can receive query from this VMDC portal, and this is quite nice to use the content of the database in codes, for instance, if you want to use things in a more automatic way. We are trying also to develop the hot pH infrared spectroscopy database. Maybe it will have a nicer name than this one. If you have suggestions, you're welcome. So that we can report all the band measure, the evolution with temperature of the position, width, and intensity. And I hope I convince you that to progress on the analysis of the aromatic infrared bands in the context of JWST data, you need to have a detailed description of the interaction of paths or any relevant carrier. If somebody wants to come with another carrier, fine. With UV photon. Also, you need spectroscopy at high temperature or high internal energy. You need to address chemical diversity, and it's very important to work on the synergy between experimental theory and observation, and this is really the PCMI spirit. And I added a to-do list, but it is not exhaustive. I'm not going to comment it, but for people who want some homework. Okay, thank you very much.